So today's speaker is Amira Abbas. Amira is a PhD student at the University of KwaZulu-Natal in South Africa. She's also affiliated with the Google Quantum AI team and has previously worked for IBM Quantum. Amira's PhD research is on quantum algorithms with a particular focus on quantum machine learning. In 2021, Amira published the seminal paper called The Power of Quantum Computational Networks, which boosted the field of quantum machine learning to new levels. And today, we're very happy to have Amira Abbas here with us and to hear about your work, Amira. So with that, the virtual floor is yours.
Awesome, thank you. Yes, my Wi-Fi I think cut out, so I missed my introduction, but that's okay. Thank you so much, and yes, thanks for inviting me. I'm really honored. Let me share my slides while I talk. Yes, and you just let me know if for any reason something goes wrong, you can't hear me, you can't see the slides or something like that. But yes, thank you again. I'm really happy to speak in this forum. It's quite an honor. I've seen some of the other speakers and yeah, I just don't know why you asked me to speak, but I'm very happy and I'll take the opportunity. Okay, so today I want to tell you a little bit about this thing called the effective dimension. And basically what it is just like an idea to understand the statistical complexity of a model. And I wrote machine learning model, but really we can think of this quite generally as any kind of classical or quantum model, as long as the output is a probability distribution. These slides are branded IBM because this is a lot of this work is from when I was a pre-doc researcher there, but I am now, yes, a student researcher at Google and hopefully finishing up my PhD at the University of KwaZulu-Natal in South Africa. So this work was in collaboration with David and Stefan from IBM and also Alessio from ETH. And it was quite an honor personally to work with these people, especially Alessio, because you might recognize he's Fields medalist he won the Fields medal, not the most recent one, the one before, for optimal transport and machine learning. So for me, like, it was really nice, good luck and timing to work with him. And yeah, I'm excited to tell you a little bit about what we did. And before I start rambling on about the effective dimension and what this means, I want to just quickly, because I know not everybody here is looking or thinking about this idea of quantum machine learning. And I think a lot of people also think it's overhyped, and people have a misunderstanding or a misconception that it's going to solve every problem in machine learning. It's going to be so much better, but really, I think there's so much we don't know that we can kind of reduce it to this idea that that's just in like one formula here, which everybody will be familiar with in this audience, and that is like ultimately what we're trying to do is we're trying to do some optimization problem. And if we think of X as like some input data for a particular problem, which happens to be like a machine learning problem, let's say like labeling pictures, for example, what we want to do is we want to learn a relationship between inputs and outputs. And in a quantum machine learning setting, what we really think about or typically think about is parameterizing some unitaries or some operations. And then, like we have some observable that we care about that maps the state to some output that we're interested in for a machine learning task. So yes, when people think about quantum machine learning, it's really like just this idea of how do we tweak these parameters such that we can like get an output that matches an output that we would expect in nature to model a specific task. And typically in machine learning, we optimize these parameters through gradient-based methods. So we can calculate gradients of this function and then like try and do clever things to optimize it to get to minimize a certain cost or loss function. Okay, so so now if there's anything that I would like you to take away from today's talk is just a couple of things. So I'll talk about this idea of an effective dimension. Sometimes I say local, sometimes I say global. I explain the difference, but really it's all roughly the same idea. And the few things that I want to hopefully convince you of today is that, so intuitively, you can think of this effective dimension as a way to measure redundancy in a model. So how many parameters, if I have a parameterized model, how many of them are actually useful? The second thing that I want to convince you of is that it's a good measure of a capacity of a model. And I'll explain a little bit what this word capacity means. And lastly, this is a little bit of an ask, but I want to try and say that the effective dimension gives us good insight into generalization of a model. And all that means is really like, it will give us an idea of how this model will perform on new data, how it will generalize on new information and new data. Okay, so if I manage to convince you of all of those things, then, you know, hopefully you will think that this effective dimension thing is really cool. And this is something that, yes, was not developed by me. It was something that was posed by Alessio in like a random 2-page arXiv paper that came out. And we thought, oh, this is interesting. Let us try and develop it a little bit further and maybe also use it for quantum models. Okay, so first, very quickly, I just want to like give a high-level idea of generalization and capacity and what this means in machine learning language. So generalization, we can think about nature like has these rules that govern in relationships between inputs and outputs. So for example, there's some true function or true mapping, which I call G here, that takes in some inputs X, and then there is a mapping that maps it to Y and output Y. So like, for example, in a machine learning task, this could be like some pictures of animals, and the mapping then maps it to the labels, for example, cat, dog, and so on. And now, of course, in real life, we don't know perfectly this true mapping. So we try to approximate it with some function, and this function is typically parameterized. At least in a machine learning setting, it is parameterized. So we try to approximate the true labels, the true outputs with a parameterized function. And so when we do this, we try and, let me just minimize my video, sorry. Okay, so when we do this, we typically like say, okay, we get some data to try and develop a function and train it. And, you know, like kind of, let's say the task is we get lots of pictures of flowers and we want to map it to the outputs, the labels of flowers. So we train on real pictures of data, real pictures of flowers. And then we use new samples, new data, new information to try and see, okay, what is the error that we make on these new samples after training and tweaking our parameters such that it fits our training data. Then we take new samples and we say, okay, well, what does this look like? So we can try and understand true errors that exist in our model class. So just to reiterate that, if you say, okay, I want to model this task of flowers, inputs and outputs with some model class, some function, let's say this is a neural network, and this neural network takes in some data and it depends on some weights and parameters. Then there will be some inherent error associated with my model class, because like I said earlier, like we don't know what the true nature relationship, like the true function in nature is. We try to approximate it with a neural network in this example. So generalization error basically tries to make statements about like the performance of this model class. And how we think about this in a mathematical sense is there is some true error that will be associated with the class of functions that I pick to model the task. So there's going to be some true error, but I don't know what that is. So I can approximate it with some training data. So N here is like, you know, number of data samples. And so I'm interested in this like interplay between like this true error that exists in my model and then approximating it with some data. So this difference here is usually like called the generalization error gap, or generalization error if you just want to think about it loosely like that. And if I have, you know, kind of models in this very large space of models, what I'd be interested in is like the supremum of this difference for a particular theta, particular parameterization, a particular set of thetas that exists in this larger parameter space. And then to say probabilistically that this difference is greater than some quantity and understand how to bound this quantity is really the best way we know to understand the generalization error of a machine learning model class. So how this is usually done is by, oh no, I've got a notification that my internet connection is unstable. Hopefully you can still hear me. How this is typically done.
Sorry, I've got a quick interruption question here. There are actually two anonymous questions in the chat that might help.
Okay.
So
sure.
The first question is, how do you quantify errors? And the second is, can you give an example of a true error?
Okay, sure. Yes, this is a little bit of a a tricky thing to understand, right? So how do we quantify error? So there's different ways, and I think like the easiest way to understand empirical error is just like through a supervised machine learning task where you have data available to you. So you've got the inputs and you've got the outputs. And if you have a loss function, so there's a lot of things that I've unfortunately left out of, of this due to time, but like you can say you've got some function that compares your model's outputs to true outputs. And by true outputs, I mean outputs that you have from data that you have available to you. So you have a function that compares your model's outputs to your true outputs. And then we can use optimization techniques to go back and tweak the model's parameters to try and get the model's outputs to be as close as possible to the outputs that we have that we know come from true data, from the true function. So this is what I mean when we can like try and approximate the error empirically. So if we have data samples available to us, we can come up with a function that gives us an output prediction. We can compare that prediction to a true sample, like the true output that it should be, and then we can like go back and tweak the parameters. So in doing that, like neural networks have become so good that we can throw billions of parameters in there, and they can fit like basically very complicated, basically any complicated relationship that exists between inputs and outputs. We can kind of artificially get this thing down to zero even to try and then understand what this quantity looks like, what this true error looks like. And that is why the right-hand side of this bound is so important, because we want something very tight here to tell us how this true error behaves. So I hope that was like a little bit of a like answer to some of the questions, but maybe it will become a bit clearer later on. Yeah. But please feel free to ask if it didn't to continue asking. Yeah.
Thanks. We'll see if we have follow-up questions in the chat.
Okay.
But thank you.
Okay, cool. Sure. Okay, perfect. So yes, so this is like this generalization error, and yes, we want to try and understand its behavior. And so what is the leading approach in machine learning is like to try and bound this quantity typically by some notion of capacity. So this is this thing I mentioned earlier. And this notion of capacity usually just tries to like incorporate the size of your model space, or your parameter space. In this case, I wrote it like this: some size of the hypothesis class of your model. And also it should depend on the number of training data that you have available to you, so that as you start to increase the number of training data, usually this bound should get, it should improve. So this thing should get, yes, it should get better, it should get tighter. Okay, so what is this thing on the right-hand side, right? So capacity. And I think this goes by lots of different terms, which a lot of us will know, like statistical complexity, expressivity of a model, the power, and so on and so forth. But we can really just think about it as how many functions can my model approximate? So the higher the function, the higher the capacity, the more functions my model can learn. So neural networks, for example, are known to be universal function approximators because they can kind of like in certain limits, they can approximate any function. So they have the potential to have a very high capacity. Okay, and so someone quite naive might think that a higher capacity is always better, right? So why not just always design models such that they can have, this ability to approximate anything? And this is a super non-trivial question and thing to think about. And the answer is like, it's not always better to have a higher capacity, but it also depends what we are thinking about in terms of capacity. What does capacity even mean? So this like statistics 101 diagram will say that, like, okay, let's say we've got capacity on this axis here, this x-axis. Then there's this typical like trade-off between how simple your model is and how complicated your model is, and the bias and the variance that it will then have. So for example, if you have a model that's very low capacity, right, so it's not very expressive, it hasn't looked at enough training data or like enough information to learn a true relationship that will exist between inputs and outputs. And so the error associated with it will be quite high. So that's the green curve here, is this generalization error that I spoke about. This will be quite high. And so we say that the model underfits. And then on the total opposite end of the spectrum, if we have a model that's super expressive and fits every single training data point almost perfectly, Then when we look at its performance on new samples, we find that it doesn't generalize well because it's overfitted the data. So it's got a high variance on new data points. So the idea of finding a model that's in the sweet spot, this optimal capacity, is something that's quite important, but how do we actually measure capacity is an even more confusing or bewildering question, I think. And the answer is largely, I think, still trying to be figured out. So obviously this idea of capacity is important because it gives us an understanding of generalization error. If we can like show there's the generalization error bound, and this bound is, you know, is pretty good, then we can understand a quantity that relates errors of our model to like actual tasks. So so yeah, so how do we measure this? And like I said, I think this is still open. This is a very active area of machine learning research. And so I don't want to tell you that the effective dimension is, you know, the best way or is the way to think about a capacity of a model. What I want to say is just like give you some ideas of properties that a good capacity measure should have. And this is in no way an exhaustive list. I think these are just some of the important things which the effective dimension happens to satisfy. Okay, so the first one, of course, is like this bound needs to hold so that we can understand, you know, this true error that's associated with our model, and having a better bound, of course, with a capacity measure that we choose would, of course, be more favorable. So the first thing is to prove this bound actually is true. And I think most people just like kind of use general concentration inequalities and a lot of simplifying assumptions, and you know, this is not typically not too difficult to do if you propose a capacity measure that's reasonable. The second property is that your measure that you propose should be scale invariant, right? So like remember now, the capacity measure should tell you how expressive your model class is. And now if I multiply, let's take a neural network, and if I multiply a neural network by let's say like a constant factor, this shouldn't change. If I multiply the weights by a constant factor, this shouldn't change the expressivity of the model, right? I mean, because you have the same model, you're just changing the weights by a small amount, whatever. So the measure of capacity should be scale invariant, be invariant to these kinds of inconsequential changes. And it turns out a lot of originally proposed or some originally proposed capacity measures did not have this property. So this is a bit problematic. It should be, the measure of capacity should be able to incorporate finite data. So this is a practical constraint that we have in real life. And if we can incorporate that would into a capacity measure, that would make comparing models so much better, so much more real, instead of certain capacity measures that try to understand like the space of the space that a model's functions can kind of learn. It tries to do this, and sometimes like capacity measures can be infinite if you look at things in a weird way. And then what does it mean if two models have infinite capacity? How do you compare them? So it's not so meaningful. Something that took me maybe like a full year to grasp was also that this notion of capacity cannot be thought of in isolation. So like when we're trying to understand generalization error with capacity, we can't just think of this capacity measure as trying to understand the size of your model space, for example, like the space of functions that your model can learn, represent. There are so many things that come in, and the learning optimization algorithm, for example, is one of them, that then restricts the space that we have access to. So what am I trying to say here? So let's use, for example, the VC dimension, which I think a lot of you will know. The VC dimension tries to basically, okay, this is a very bad picture, but it tries to understand the size of your model space, the full size of your model space. So you can think of, for example, I'll use neural networks again. You can think of like a point in this space as, let's say your neural network outputs a probability distribution, right? So you can think of a point here as a probability distribution for a particular set of parameters. So a particular theta is how I noted it, right? So this full space here is like for all possible parameterizations, what like the model looks like, behaves like. So the VC dimension tries to quantify how large the space is. But like there's a lot of research coming out that shows that, like, let's say I randomly initialize my parameters of my neural network, like somewhere here. And then I do gradient descent and use gradient methods to try and optimize and find better parameters, better solutions to minimize a loss function to get a very low error. What this means is that I'm actually restricting the space that I have access to by imposing a certain optimization algorithm, a certain like learning algorithm. So in reality, like trying to understand this full space of the model is not really so relevant, not really so clever, because it like we actually restrict ourselves to a smaller subspace of this model space. And so like imposing this like these restrictions that comes through like the optimizer, the data, and so on, we should actually have a capacity measure that tries to understand this restricted model space, because this is in reality what we have access to. Okay, and then the last thing is I explained this like regimes of underfitting and overfitting. And if you want to have a good capacity measure that gives like a nice bound with generalization error, then it should like also correlate with these regimes. And yeah, the details of this is not so important, but like as you train your model, you can kind of show that you know, this underfitting behavior happens if you haven't trained on enough data, and it starts to overfit if you've trained on too much. And so if you then like plot your capacity measure, whatever that is, it should correlate with these two regimes. Okay, so some of the work that we did was basically to show that the local effective dimension satisfies all these criteria, right? The criteria that I just mentioned to you now. And if you're interested in this like idea of capacity and studying this, you know, there's lots of different ways to think about capacity. So I mentioned VC dimension, but there are also like beautiful other ideas out there that incorporate totally different and really amazing kind of mathematics and statistics. And so I can point you to in particular this really nice review of capacity measures that are out there, and also like some analytics like studying them, and sorry, empirical studies about them. Okay, so now finally I can tell you about the effective dimension, and please let me know if I'm close to like the end, because I really want to have a discussion with you and, you know, hear your thoughts. And so yes, I want to try and finish a little bit early. So the effective dimension, I always put up this picture of clouds in the sky, because I think of the effective dimension in this like intuitive way, and this is how I explain it to my parents actually, is like, you know, clouds are in a 3-dimensional space, but like they don't occupy the full space, right? They occupy like a fraction of the space. And so you can kind of think of machine learning models that, you know, which are over-parameterized. So they're in this very, very large space, but how many parameters in this very large over-parameterized space, how many of those are truly active or you know, alive in this high dimensional space? So what is the true size of my model in this very high dimensional space? And so the effective dimension tries to capture this idea. And in particular, it tries to capture this idea by using a scale parameter. So in some sense, it's very closely related to like a fractal dimension, where scale matters. Scale actually influences the dimension. So so we use this idea of the effective dimension to try and compare what we call quantum neural networks, but this is probably a very bad name. Just think of it as like, you know, you've got some input vector, like this can be a classical vector, which you then encode into a quantum state, or this can be a quantum state that comes from some natural process. And then you apply some parameterized unitaries, and then you make a measurement. And all we say is that the measurement outcome is a probability distribution over our outputs for some machine learning task. And we compare this like quantum neural network to a classical neural network, which they both have the same input size and the same output size, and they both have the same number of trainable parameters in them. So this is like, well, how we do our comparison. Whether this is fair or not is still also something that's, you know, totally subjective. So like this might not be fair in some ways, especially because, you know, there are like nonlinearities that are injected in classical neural networks, which quantum models don't really have. And yeah, there's a few other arguments that could be made, but we make this comparison and we look at the effective dimension on each side. And what we found was that consistently these quantum models seem to have higher effective dimensions. So what does that mean? And we'll get to that a little bit later. Okay, so the effective dimension, I'll just give you a very quick explanation, and then we can like run through the rest of the results. So if I have some model, and now I have like the parameters coming from parameter space, right? So let's say like a uniformly sample a set of parameters. So theta, let's say, is like a d-dimensional vector. That's the parameters for my model. But now, like if I, for example, like just do a small uniform shift in my parameter space, this doesn't necessarily correspond to a uniform shift in the output of the model space, right? So there are these two spaces that that are very important and very very closely related. But what we're interested in is like model space, right? We want to know how does things move, or like how do things move in model space, so that I can adjust my parameters to minimize a loss function to get like better results. So model space, again, this is a bad picture, but you can think of like a point here as a probability distribution for a particular parameterization, and the parameterization is like a fixed theta, set of thetas. Okay, so how do we know, like how do we think about how to alter like, you know, our parameters in parameter space? How do we wiggle our parameters such that we like, you know, kind of understand the behavior in model space, we understand the repercussions of what we're doing in the space that we're actually interested in, because typically we want to like minimize some function that depends on this space here. So the answer to traverse between these spaces is given by a metric, the Fisher information matrix. So this Fisher information comes up in a lot of different settings, and I'm always so amazed personally by how many different ways you can think about the Fisher information. And every time I think I kind of understand it, you know, like there's a different lens, and then I'm like, oh, actually, there's another thing about it that I didn't realize. So it's really quite a useful metric that serves as a distance in model space. So it gives us a notion of distance and a notion of size. If we think about like volume, it gives us a notion of size in the space that we're interested in. So the Fisher information, you can think of it in many different ways, but I just write like the formal definition here as it would be expressed in the machine learning language. So I've got like P of x, y, theta, and P is basically like, you know, I had this f of x theta earlier as to represent my function. If I assume a probability distribution as an output, then I'm just writing it as P now. So it's P, and then X and Y is just inputs and outputs training data. So I'm just saying like I've got probability distribution that takes in some training data, X and Y, and it depends on some parameters, right? So this is just a function that's probability, gives us a probability distribution, depends on some parameters. So the Fisher information can be thought of as like an outer product of the log of this probability distribution and the partial derivative with respect to the parameters, right? So it's a D by D matrix, and it contains these elements of these partial derivatives. And yeah, we can think of it as an outer product. Some people also think of it as like this giant covariance matrix, where like it tells us how sensitive our model is to changes in certain dimensions or directions and certain thetas. If we change them, how sensitive, you know, things are in this space. And again, this is, yeah, not very good pictures, I'm sorry. So I hope the intuition comes through. Okay, so yes, why did I put this slide back here? Oh yes, because I wanted to say that we consider in this analysis the classical Fisher information as I defined it here, right? So I know there is also like this notion of a quantum Fisher information, but this is not the thing that we use or look at in the effective dimension, which I'll talk about now. But they are closely related, so one could, in principle, swap the two around. Okay, so finally, the equation for the effective dimension. And I think it's actually a rather nice, neat form. Well, not neat formula, but in terms of like what it's trying to say, I think it's pretty neat. So if we look in the numerator, we've got basically here like the square root of the determinant and the Fisher, right? So if you remember, I said that this gives us a notion of volume in model space for a particular parameterization, a particular theta. And now we're averaging over the full parameter space. So we're kind of getting like an average size of model space, and we're normalizing it by this V theta here, and this V theta here is the volume of the parameter space. So we're like taking a ratio of model space to the parameter space to get an idea of size, and this of true size, effective size. And this kappa here is a very important little thing that we introduce, or we like manually kind of inject into this effective dimension idea. And this kappa depends on n, and this little n is basically like how many training data samples do I have available to me? So you can think about n actually as a scale parameter that I mentioned, like, you know, this fractal dimension depends on scale. the number of data here is a scale parameter that allows us to zoom into a model space. So as we increase, and we can increase the resolution at which we can see our model space. So, and now this effective dimension also has many different ways to interpret things, because the Fisher information is also so like diverse. And so one such way is, okay, so the Fisher is a D by D matrix. One such way we can think about it is because we've got determinant, square root of a determinant, the eigenvalues of the Fisher information is what is important to us, right? So the effective dimension essentially counts the number of eigenvalues, or the number of dimensions or directions that are larger than a certain threshold. And this threshold is determined by our scale parameter, the number of data available to us. So it tells us, like, for a given scale, this is how many like dimensions or directions are actually like important. And what that means is that this is how many parameters in my model are actually alive, that are actually useful. So yes, how many parameters are useful. Okay. So one thing I just wanted to now then go into is like why this effective dimension satisfies the criteria of being a good capacity measure. So the second follow-up piece to our work was we realized we studied this quantity for classical and quantum models by looking at the full model space, but you can actually like sample an epsilon ball around like a particular theta, particular like parameter set, and restrict your model space. And then we define this like idea of a local effective dimension. But you know, essentially these things are the same thing, so it's not too important to worry about. The second thing is like this effective dimension is inherently scale invariant because the Fisher is normalized. So we take the normalization with respect to the trace of the Fisher information. So this is nice, so that if we like have these inconsequential transformations of parameters, this shouldn't affect the effective dimension. It is inherently designed to incorporate finite data because we have the scale parameter, this little n. And then I guess probably the biggest theoretical result of the work was like that it can actually bound the generalization error, right? So showing this bound holds was done in the first piece of work. And again, like the details are not so important, and all these constants and things in here is if you're interested in like understanding, please, you know, that it's in the appendix of the papers. But it's actually, I think, if I'm not mistaken, it follows pretty straightforwardly from results that already exist. So there are relationships of this quantity, this generalization error, to something called a covering number that can cover the space of functions, right, that a model can express. And so like we relate the covering number to the effective dimension, and then the bound kind of follows pretty trivially after that. We don't know how good it is in certain regimes. Like this is still like something that's open that we should investigate. But yes, at least this is like in general the relationship that holds. And then the last thing,
a quick
yes.
interruption, if
Sure.
So
no
this
problem.
is another anonymous question. Can you comment on the complexity of calculating F, so the Fisher information?
Yes, sure. Okay, so that's a good point, right? Because you want your capacity measure to be something you can actually calculate. And in the deep learning regime these days, where you've got like billions of parameters, if F is a D by D matrix, there's no way that this is like feasible to calculate this matrix efficiently. But luckily, there's a really, really nice result that approximates the Fisher information such that you can calculate the eigenvalues efficiently. So there is it's called the KFAC approximation. I think it stands for like, what does it stand for? Kronecker factorized. I can't remember the abbreviation, but if you Google KFAC, it will come up. And what it is it's just a block approximation of the Fisher information, and it shows it like converges to like the right results in certain limits and so on. And so we take this KFAC approximation in our numerics, and you know, if you're like doing this block approximation of the Fisher, you can like calculate the eigenvalues of the blocks, and then you know, take the products and stuff like this. It all works out very, very nicely. So you actually don't end up needing to calculate a D by D matrix. You can calculate these sub-block matrices, which are actually quite small. Their size in the case of neural networks depend on the size of number of parameters per layer. So this is also like really efficient. And then you can take the eigenvalues and kind of and you end up, I think, multiplying them if I'm not mistaken. So yes, so the efficiency there is fine in terms of these numerics. So yeah, this is also something that we spent a lot of time on, because we were like, you know, if we're going to extend this to larger models, how can we do that? Thankfully, through this K-FAC approximation, things work out really nicely. So there's also a little snippet on the computational efficiency of calculating this measure in the second paper, if you're interested in reading the details there.
All right, great, thank you. Just a quick follow-up question. So does this mean that this whole equation can be calculated efficiently?
Yes and no, right? So I'd like to say yes, because you know, we managed to do it in the second paper for models with, you know, a couple million parameters already, and it runs very, very quickly. But there's a catch there. So depending on which version of the effective dimension one is looking at, then efficiency comes into play. So if you're looking at the global, which is the one that I mentioned that tries to understand like sort of roughly the full parameter space, the full model space, then this one is not going to be so efficient, because you're going to need to calculate, you're going to need to sample many theta parameters to get an accurate sort of representation of the full space. But if you're looking at the local effective dimension, then yes, this is very efficient, because you're not trying to get a sort of representation of the full space. You can train your model and just look at the final parameter set and sample an epsilon ball around there, or even just calculate the local effective dimension with the final parameter set, with the singleton. So so that is why you know, we actually extended the work to look at this local effective dimension to make things more efficient, and also capture true true behavior by incorporating the learning algorithm. So this is the sort of it depends answer. Yeah. Okay, great. Okay, so yes, the last criterion was like, does it capture this over and underfitting behavior? And there's a really nice paper, which is terrible that I didn't cite it here. That's very bad. So it's I think it's called Rethinking Generalization in Machine Learning. In machine learning, I think it's the author is Zhang et al. And what they do is they take a data set, and they artificially start to introduce noise into that data set. So they do that by shuffling the labels around. So they start to, like, you know, train models on data relationships, inputs and outputs, that become increasingly noisy. So they're like not actually true, right? So in doing so, like, you know, and like I said, neural networks are so expressive that you can train them down to zero error, right? By forcing the parameters to learn false relationships. So you can do that, and then you know your model is not training on true data. And then you can look at its performance when you get like out of sample data that you haven't trained it on. You can look at its generalization error. So all this experiment does is it says, if we look at the right plot, this is the one that's important here. It's saying that as I increase the noise in my labels, so as I randomize my labels for my training data of my model more and more, then my error for the model on new data, on new samples, will start to increase. So the generalization error starts to increase. And this makes sense intuitively, right? If I'm training a model on nonsense, and then I want to know how is it performing on real data, on new data that it hasn't, of course it's going to do badly. So as you like increase the randomness in your data set, then your model does poorer and poorer on actual data where, you know, true relationships do exist, but your model has learned noise essentially. And so like the effective dimension tracks this overfitting behavior quite nicely. And yes, okay, so this just like ticks this button. We did a few more like empirical verifications to see if this correlation between the effective dimension and generalization error holds for different optimizers, different data sets, and so on. And importantly, we normalize the effective dimension, right? So the effective dimension, the maximum it can be is the number of parameters d, right? So we can go up to this, and then we just kind of normalize what it is by d. So we divide by d to get a way to compare models. Okay, so yes, I know I ran through a lot of information very quickly, but hopefully, you know, you'll be interested enough to see like that the effective dimension satisfies properties that we think are quite useful for a capacity measure. And now, lastly, what I just spent the last 2 minutes, 3 minutes on is like, what does this actually mean for quantum models now, right? Because like I said to you, they have high global effective dimension. So what that means is that like a lot of parameters in the model space for a quantum model seem to be a lot more active. Like these parameters seem to be a lot more active in the quantum setting versus the classical one. And why is that? And in particular, if we look at the histograms of the eigenvalues of the Fisher information of a classical neural network and a quantum neural network, what this distribution is telling us is that for a classical neural network, most of the eigenvalues are 0 or very, very close to 0. So that means that like not a lot of directions or dimensions are important in a classical neural network. There are these large occasional spikes and large eigenvalues. So there are these directions in your model space that the model is very sensitive to. So so this is interesting, right? Because it says like, okay, the landscape, if you think about landscapes now of your model space, the landscape is mostly flat, it's mostly flat here. And then there are these few spikes in a certain directions that are important. But now on the quantum side, things are not so flat, right? A little bit like kind of choppy. And this is like represented with a sort of more uniform-ish spectrum. So why does this happen? And does this always happen? Or is it just like something inherent to the models that we picked or the size of models that we picked? This is also like, you know, a criticism. So this might not hold true for every setting, but this is interesting. And in particular, what I think is interesting is this result here for classical neural networks is something that's very well known. It's something that actually people have shown to correlate to good generalization performance. And this is so counterintuitive because what they show is that, in particular, like this result from Peter Bartlett, who subsequently, yes, is there a question?
Quick interruption.
Sure.
Yeah. So on your previous slide
no
here, you have an inset and sort of main figure, and the scales of the x-axis are different. Can you comment on what these, what the x-axis of the inset versus main figure means?
Sure. Yes, sure. So my apologies for not explaining. So this little figure here is just basically taking this first bin and just looking at it, zooming into it. So looking at the counts of the eigenvalues inside this first bin. So if we zoom into like this one here, so you can see this is like saying how many eigenvalues are between 0 and 5, and then we zoom into this thing, and then we see like, okay, still for, you know, in this bin, there's still most of them are very, very close to 0. And whereas on the quantum side, if you zoom into this first, like, first interval, first bin, or whatever you want to call it, you can see it's a lot more uniform still. So the point of that little subplot is to just show that it's not so close to 0. Yeah.
Okay, thank you. And another question. So these non-zero elements in the quantum neural network, can you comment on if this is related to the many local minima in VQE systems?
Yeah, good question. I mean, if you just think about like what this is telling us, it's telling us that, you know, like the space is very there's a lot of curvature in the model space, right? So yes, why not, right? Because with many local minima, you know that this is exactly how the model space looks. At least how I envision it is always like, when I'm swimming, I always think of like the waves in the pool as this like model landscape for quantum models, and particular like VQE with these lots of many local minima. So yes, it could be a property of that. It could also change depending on how you set up your model, right? So the models that we chose for these quantum neural networks very much look like these VQE setups. So yes, I would say it could correspond to that behavior. Yeah. Okay, cool. Thank you for the nice questions. Okay, so I was saying about this result here, this all these eigenvalues concentrated around 0 for classical neural network. And yes, it turns out they're actually super important. And this result is really, this paper is a really nice paper. So Peter Bartlett, who I'm super lucky, like actually got a desk sitting next to me the other day we managed to chat about. So this paper basically says that for linear models, at least, they managed to show this like analytically, that these this behavior here is a lot of parameters are redundant in the model, but there seems to be a need for them because they the intuition is they kind of soak up noise that exists. And so this is like so weird to me, because you blindly think like if you're adding more and more parameters into your model is going to overfit and perform badly. But neural networks don't do that, right? The more parameters we throw into them, they don't overfit. They still kind of perform really well. And the result here kind of says that this redundancy needs to be there for this generalization behavior to be, pretty good, because those parameters that we think are inactive, they're not harmful to the model. So this overfitting is benign. It's not harmful. And this is the premise of this paper. And this then encouraged a few other works in the quantum field to come in and then say, okay, well, let's examine the class of functions that these VQE-like models express, right? So there was a very nice paper by Maria Schultz, who's also one of my PhD supervisors, which is quite nice. So she and a few others went and said and investigated these typical parameterized circuits that we look at, and said that we can actually write down the class of functions that they express as partial Fourier series in the data, and how we encode them determines what this Fourier series looks like. And then they went on to show like what overfitting looks like and how it can be benign in a quantum setting as well, with this follow-up paper with her and Evan. So this is nice to see that like people are actually making these links. Okay, so that still doesn't really answer the question of like, okay, what does it mean if we have a lot of active parameters? And I still don't actually know. And if we do, if we know that quantum models seem to have this higher capacity, how do we build our circuits and our models to control for that overfitting behavior such that we get good generalization performance? And a really nice result that I want to highlight, and then I will conclude, I promise, is from Matthias Caro and a few other people. And they basically showed a generalization error bound that exists for these VQE type models again. And this bound says that the generalization error, and alpha here is what I call theta, so like this trained parameter set, so this trained model, this trained quantum circuit, its generalization error scales like something like the square root of t over n, and t is the number of trainable gates that you have in your model, and n is the number of data. They just call it like number of data. So this is quite cool, because this is telling us that if we have a model that has like polynomial number of gates, like trainable gates, then we only require amount of training data that's also polynomial in n, where lowercase n is the number of qubits. So this is quite nice to get like good generalization. So this bound is quite interesting. Okay, and then the last question, which is not so important, but it's just like I'm wondering if overparameterized quantum circuits will behave similarly to overparameterized neural networks, because we get all these beautiful theoretical results that come with overparameterization. In fact, models start to look more tractable through overparameterization. There are these implicit regularization that comes in through training and so on and so forth, but I won't spend time on those details. I just want to say thank you very much for listening, and yes, if you're interested in this stuff, please feel free to reach out. I have subsequently like changed topics now that I'm working with Google, but yes, this is still very interesting to me and comprises most of my my PhD. So thank you for listening.
All right, great. Thank you very much for the talk. I had a quick question for you. So in the active parameters, you sort of discard the inactive parameters. Are these parameters, do they truly contribute 0, or do you have a threshold below which you say this is not active enough, and so we'll truncate it from the model?
Yes. Really, really good point and question. So if you remember, there is this kappa here, which I at least wrote here. Okay, so you can think of this as just like as a factor that depends on n, right? The number of data, and so the number of data to us determines exactly this threshold of where eigenvalues start to become important or not. So there is a threshold in which we say parameters become active, and this depends on like the scale, the resolution parameter, which in this effective dimension definition is what we kind of relate to the number of data. So yes, there is a threshold, and that depends on the number of data available. Yeah.
All right, great. Thank you very much. So Professor Mike Payne has just a comment. This isn't a question, but he says, okay, so the task of sampling the entire model space M is what nested sampling was developed for.
Okay, I don't know. Okay, I don't know what what nested sampling is.
Maybe
Yes,
it's for
but
some further
yeah,
reading. And so,
yes.
okay, we have another question here by a PhD student, Hao Mu.
Yeah, I can hear you.
Yeah.
And yes, my question is because like the Amira's talking about in classical models, she will made some situations that overfitting. And I'm asking if like if we increase, like we have more parameters inside like a quantum circuit or like a quantum neural network, where we also, because when we have a lot of parameters, we will also like made some like barren plateaus in like training. So I think that also could this also correspond to like what is like overfitting situation? Some parameters do not contribute a lot to like your training, but we still need them to get like our like a final state, like something.
Yeah, yeah. I think it's such an interesting question and something very difficult to grasp intuitively, at least for me. So I think like a lot of people from quantum control maybe have the answer here already, right? Because I think then they look at like limits of having infinite control with like, you know, we can kind of imagine it as an overparameterization and taking like number of parameters to very, very large scales. And then things start to smooth out again, right? We know that things start to look nice and we get like convexity in the optimization landscape. So I think there is it's a very delicate question of, and in particular, I just want to point you to the last paper, this one. So tractability through overparameterization. I think that this is something so interesting for us to look at. So this paper looked at this idea for linear models, and they take like a number of parameters to be infinite, and they show that things like very nicely smooth out, and we get like we get interesting desirable behavior. And I feel like we can do something very similar for the models we use in VQE, for example, because essentially they're linear models in a feature space, right? So they're in a high dimensional quantum feature space, and we're doing linear classification essentially is what we're doing with VQE. So I think there's some interesting work to be done to extend this idea, and we tried, in all honesty, to like look at this and you know, use it as a tool to try and work backwards and say, how do we design quantum models so that they can perform better in terms of generalization? But yeah, it gets very difficult very, very quickly. And yeah, so to answer your question, I think that my gut tells me that yes, a lot of the behaviors when we overparameterize quantum models will look similar to like some properties that we get specifically for like these results here in this paper. But also, like, you know, we know things are so sensitive to how we think about data, how we encode data into quantum states and so on. So I think it'll be very difficult to say, like, for a specific use case, this is where it's useful and this is like a task it can solve. I think that will be very difficult to show, and that's what everyone is trying to do, right? So yeah.
Thanks. I see the point. I'm
great.
working. Thanks.
Thank you. And we have one last question by Chris Long, who's on the panel as well.
Hi. Thank you for a great talk. I'm sorry if you've already answered this. I turned up a few minutes late, but I took away that the quantum models have a higher capacity, but I wasn't really sure whether this was a good or a bad thing, or if there's just like positives and negatives to that. I wondered if you could kind of summarize what the implications of higher capacity are.
Yeah. I mean, yes. So this is exactly the crux of you know, all this investigation, right? So yes, there seems to be this inherent higher capacity for these quantum models, and I don't think we fully understood whether this is going to be good or bad. So I think in like, you know, naively in our first work, we were like selling this as like, oh, you know, it's more powerful, it's like this, it's like that. But if we look at, you know, these generalization areas of models, a very delicate thing to understand, and it involves a lot of interplaying variables, right? Like the learning algorithm, this, that, how you measure capacity. And so I think it's not easy to just say it will lead to overfitting, because at the same time, we don't have the hardware to test scales where overfitting can really happen, right? So far, like most of the studies, so this is an interesting paper because it's a first in that it's like an analytical study and it could only happen for linear models, but all the other investigations about capacity for neural networks can be investigated empirically. So a lot of intuition and theory was informed through empirical studies. With us on the quantum side, we have empirical studies for very small models, and that's where like that's where I have this spectra here. But this is not an overparameterized regime. This is an underparameterized regime. So to push that to an overparameterized regime, we can't do that on the hardware. We're going to need to try and study it analytically. And yes, I don't think we have an answer for what it will mean if our quantum models are still, even in those overparameterized regimes, more powerful or more expressive. Maybe it means we don't need that many parameters in our model. Maybe it means we can be more resource efficient. I'm not so sure, but yeah, so it's a very good question. So,
Thank you.
Great, thanks. David, did you have a comment? You raised your hand.
Yeah, maybe just a final quick question. We have a bunch of PhD students and master students that are really interested in these topics. Where should they go and kind of look? What's the thing to put attention on?
Yeah, so let me stop sharing. So there's a really nice summer school on quantum machine learning that was done with IBM's Qiskit summer school. So all the lectures and the material, and there's even a textbook, that's all on the website, and I can just quickly pull up the link quickly. I think that's a really good place to start because, as far as I know, it gives a high-level overview of everything that's current in quantum machine learning. And then as a student, you can kind of say, oh, I like that lecture, that was interesting. Let me go and dig a little bit further and look at the person, the research that the person is citing and take it from there. So let me see if I can pull up the summer school. But yeah, I think if you just Google Qiskit IBM quantum machine learning summer school, it will be there. It was the 2021 summer school. Oh, okay, here it is. I post the link now in the chat.
Thanks. I think
I can send it to everyone.
I found it on Google at least, so I think people
okay.
will be able to find it.
Okay. Okay. Cool.
So I think with that, Hugo, we're done with this year's quantum information seminars. Thanks so much, Amira, for this really stimulating and interesting talk.